Good afternoon. Thank you, everyone. It's a pleasure to be here again. Yes, like I said this morning, let's have a closer look on corrosion and corrosion management in and around battery cells or lithium-ion batteries. And for sure, what can we do with surface treatments? First, introduction on corrosion. What is corrosion? How do we define corrosion? And just look on the yellow highlighted, let's say, words. So corrosion, for corrosion you need metals, you need ions, and you need an electrolyte. Without this, so one of the other is missing, you don't have corrosion. And there are different types of corrosion. So the first, you see them highlighted here. So we have corrosion within the crystals, intergranular corrosion. Pitting corrosion means on the surface and going into the surface. Galvanic corrosion, so there you have dissolution of metals into ions, and then in the end some stress corrosion, cracking. So there the metal is cracked, or the surface, the material is cracked, and then corrosion is happening. What can we do against corrosion? So you see it down there. We can do coatings, we can do cathodic protection, we can change the material by alloying it, and or passivation, so a passive layer which is not due to corrosion or which is not acting in any kind of corrosion. So this is what we can do. Oops, sorry. When we look in the battery cell itself, what kind of degradation effects are there? So there's a variety of different, I use this one, different degradation effects. So effects which will destroy and degrade the batteries. So the performance will lose or will go down over time. And you see in this bunch of different effects, you see here copper current collector corrosion, sorry, and the aluminum is also corroding. So these two types, I will have a closer look. The other degradation, I will not today look onto this. So these two types of corrosion can happen in a battery cell. And where can battery or corrosion happen? I mentioned you need an electrolyte, you need metals, and you need ions. And usually you need the connection of these different medias. And they're only happening on the surface where you have metals. So you see here lithium-ion battery, here's the aluminum current collector, here's the copper current collector. And then you have various layers in between, they're explained here. And only these interfaces between these two current collectors and the battery, you have metal. So this is where you can have corrosion. That's why we only talk about the current collector corrosion. And then the ions, if this is corrosion is happening, the lithium, the aluminum, or the copper ions will go into the battery electrolyte. So this is the corrosion, actually, which is happening inside battery cells. What is the basic for this corrosion? This is so-called galvanic couple corrosion. I mentioned this morning already. So whenever you have two different metals in contact with each other, there is a potential difference between these metals. You know, maybe noble metals like silver, gold, you don't see corrosion of this. And you also know not so noble metals like iron. We know in our normal life, iron will easily corrode. You have this red rust, this red iron corrosion. So these couples in here, which we've maybe faced in the battery, will determine the speed and the amount of corrosion. And then on the other side, the second picture, you see the potential of lithium, which is the ion, which is in the electrolyte, in the battery electrolyte, because we use lithium to charge, discharge, keep the energy in the battery. And there we see how this potential of lithium is in conjunction to several different metals. So copper, aluminum, iron, and so on. And there you see, if we reach certain potentials between the lithium and, for example, the copper, you see here 3 volts, basically, you will have copper dissolution. And this meaning copper corrosion. Same for the aluminum, some areas, and other materials. So this is the basic. We need to understand why there's corrosion happening in these batteries. And what can we do? Let's have a look on copper. As I mentioned, when we have lithium combined in a metallic form to copper, there will be some corrosion happening. We saw the potential. So in this area, we will have copper dissolution. So copper will dissolve. This is you see here, over here in the pictures. Sorry, I don't see them. But when you have here in this scheme, you have lithium or lithium particles. They're in touch with copper. And if there's any corrosion happening in these contact areas, the copper will dissolve and the lithium will lose the connection to the copper surface. I hope you can see it on these pictures. And for sure, if there's no connection, no current can flow, so no charge can go through there. And this means we will lose performance of the battery cells. So this is something we need to prevent by using several passivation layers on copper, which I will introduce to you later. Then looking on aluminum. One nice property of aluminum is, we may all know, it's self-passivating. So if you have pure aluminum in oxygen, so in our environment, it will automatically very quickly passivate itself with aluminum oxide, which is a very passive layer, which is not, let's say, normal conditions undergoing any type of corrosion. When we look on this in terms of the battery, so with lithium, you see 3.5 volts is there, the stability area, the potential where aluminum would dissolve, which is quite high. So this is very good. So we don't need anything to do, basically. But there are 2 ways to also remove this passive layer, which would mean if we achieve higher potentials of this 3.5 volts. Meaning when we charge, and we charge too quick with too much power, there's a risk we overcome this potential, and then we will have this dissolution of this aluminum oxide, and then you expose bare aluminum, and this aluminum you see over here will corrode. Another way to, let's say, remove this oxide layer, which is the passive layer, is to use certain ingredients, solvents in the electrolyte, this TFSI, for example. You see over here what the TFSI is doing. So this TFSI is building some complexes, and then is also here removing this oxide layer, and then it's exposing the bare aluminum, and then we have again corrosion. So we need ways, also here we need a better passive layer which avoids these 2 effects to further enhance battery performance. There are these were the 2 corrosion effects in the battery cell itself. There are way more when we look on the bigger scheme on the battery pack systems or the modules. So you see a list over here what can happen in these areas for some specific areas and specific applications. I will highlight a few of this on the next slides and what we can do with surface treatments to prevent or to slow down or to manage this kind of corrosion. Yes, like I said, some examples. First approach is first application, the battery housings. So we look on the battery case material. More than 90% today is aluminum, so we use aluminum for the housings. What we can do in surface treatments, what we need is cleaning, surface preparation for painting afterwards, for e-coats and other materials, and also a so-called conversion coating to increase corrosion resistance. These conversion coatings, they provide a passive layer which is even more passive, let's say, than aluminum oxide. There are some applicators, some automotive OEMs who prefer steel as the battery cover. Here we need to introduce some corrosion protection. You know, steel, if you use a normal steel, it will corrode in our normal environment, so we need to protect it from corrosion and another thing we need to consider, I showed this morning already, is when we mix different materials and you use the wrong connection methods, you match the wrong materials to each other, you will have a risk of contact corrosion. So you have too high potential between the materials and you have immediately corrosion. Another thing to consider is the requirements, not only corrosion, but also, let's say, the risk of fires and so on. So there are various requirements for these battery housings. So it needs to be completely enclosed, and it shouldn't be, or there shouldn't be any risk if you soak it directly into water, which is pretty harsh. Let's say if you put something, a metal into water, the water acts as an electrolyte and you will have quite immediately corrosion or leakage. For sure we need a robust frame, even in case of collision, and to prevent any penetration. Temperature plays a role. Here we have the cooling inside. Also this cooling system offers a risk for corrosion. Again, you have a liquid. Again, you have a liquid which can introduce corrosion. And last but not least, heat. So overcharging can lead to heat up of the battery. And with this, we can also introduce corrosion into this whole system. What can we do against corrosion? This here is an example for steel. So there are different ways and surface layer treatments what we can apply. And we go from here, which is basic, and to the more and more sophisticated system. So basic is you have a cleaning step of the steel, and then you only use a zinc phosphate, which provides a basic passive layer, and then maybe you have painting on top. Let's say the painting remains for all the same. If we want to improve now this corrosion resistance for steel, we need certain steps. So we introduce a zinc nickel layer, which offers cathodic corrosion for the protection for steel, so it's corroding and the steel is not corroding. If we go further and improve it further, we also use again a passive layer on the zinc nickel, replacing the zinc phosphate. This further increases the corrosion resistance, and the most sophisticated, most long-lasting system, then in the end you use again a so-called sealer, which is again a barrier layer, which is like a sealer of the whole system, and it even increases further the corrosion protection. So depending on the requirements and the economics, you see there are various ways on how to protect steel for corrosion. Yes, the next example is contact corrosion for aluminum. So if we use screws to fixture the aluminum, you see, and I mentioned this morning, you need to choose the right material. If you don't choose the right material, you will have immediately corrosion due to different potentials between the aluminum and the coating on the screws. I think next picture is more explanatory. So if we use here fasteners which have, for example, zinc, a layer where the potential between zinc and the aluminum is quite high. So you see you have quite high severe contact corrosion. Whereas if we use a different system, zinc nickel, which is closer in potential to aluminum, you see you have even less corrosion than in the blind reference where you have plastic, let's say plastic screws. So with this, with choosing the right system, we can reduce the risk of contact corrosion and protect, in this case, our workpieces. The next example would be busbars. So for sure, in these battery packs, we need to ensure that the current is flowing from the battery to the engine or to any other consumer of electricity. Therefore, we need busbars. So busbars need to transport high current densities. So we need low contact resistance. Basically, we use aluminum or copper, which have very high conductivities. And for sure, you need to connect these parts to each other to be able to transport the current. There are 3 different types. Welding, so you force the metals to melt and bond together, where we need no coating or protection because it's like this bonding is very strong. But as soon as we use bolting or we use like spring contacts where you only have mechanical force of connection, you need several different coatings, protections to ensure conductivity or connection between these bus bars and functionality, so it needs to last a long time. Yes, here's the example for bolting. So if I bolt 2 of these bus bars together, what are the influences? So temperature and starch testing, they reveal different incompatibilities. Sorry. You see here the different metals we can combine or coat on copper and aluminum. And you see for this kind of combination, when we bolt, we should use tin. Tin is quite soft. So if you bolt it, it will also like connect to each other by the bolting force and ensure high conductivity. The same is true for silver, but for sure silver is very expensive. So tin is here the best option to use if you want to bolt different materials to each other and with this ensure conductivity. But conductivity is not the only key. We also need to ensure again oxidation or management of oxidation. And tin also tends to oxidize when we have the wrong conditions. And therefore we can achieve also again here some corrosion protection by surface treatment. We use, let's say there are 2 different approaches. You can use or you can hydrophobize the surface, so water is repelled, it's not sticking, so we don't have any liquid or electrolyte. As we remember, we need an electrolyte, water, for corrosion. Or we can again apply passive layers. You see here phosphorized conversion layer or thin metallic finishes. They offer a passive layer which prevents the tin again from oxidizing. There are few advantages, so we don't need much. We only need a few atomic layers, so it's really thin, the layer. And with this we have a very little effect on contact resistance. So with these treatments we ensure good conductivity but prevent corrosion. Yes, some tests you see here. So this is for tin protection on bus bars, some bus bars after corrosion testing. So here we have a protected tin, or these green ones, they are protected. And if we have unprotected, you see this discoloration. So after 10 minutes at 260 degrees, it's discolorating. If we go to almost 305 minutes, you see it's discolorating or discoloring. And with this, you see the tin itself is oxidizing, so meaning it's corroding. And with this, we lose the conductivity, we lose the properties we want to have for our bus bars. In the end, I think we know that this is then a failure. With the treatments, you see same testing. You still have this nice silvery look of tin. So the surface is protected from oxidation and we keep our properties. If we want to do the same on silver, sometimes you use silver, not always we use tin, but sometimes we also use silver for high requirements. Also again here, let's have a look on the different treated ones testing. So untreated silver, you see even at room temperature, when we expose it to some oxidation solution, potassium sulfur, you see at room temperature and 200 degrees the silver itself, if it's not treated, it's oxidizing, it's tarnishing. If we use some passivation products, you see this is an organic type. At room temperature we have protection. If we use high temperature, this organic one is not really protecting the surface, so we have some tarnishing. If we use a metallic one, here we use chrome layer. You see even at high temperatures we keep the nice shiny look of silver. So with this we are protecting our silver surface from tarnishing very effectively at high temperatures. Yes, then an example where we replace hexavalent chromium in copper passivation. Why do we need to protect copper? Again, if we have unprotected copper, we have oxygen, the copper will oxidize over time, and this oxide layer again is very, it's influencing the conductivity of the copper, so it has a way lower conductivity than pure copper, and we need to ensure that our copper, especially if we use it in the battery, has the highest conductivity possible. What is the current technology using? Currently we use hexavalent chromium. For you who don't know, hexavalent chromium is very toxic, it's very dangerous for the humans, but it's also offering nice properties. So at the moment the industry is using Chrome 6, but if you think about sustainability, we need to replace these toxic, these dangerous materials over time, so this is the trend. And herefore we introduce a Chrome 6-free technology, which in the end provides the same protection as the Chrome 6 technology. We have 1 to 3 nanometer thin layer of chromium, and this is then preventing the oxidation of the copper. Just a glimpse on Europe. REACH, you have copied this. As Korea, you have the K-REACH, the so-called K-REACH. In REACH, these dangerous materials, they're under supervision of the governments, the legislation. And here, Chrome 6 is not banned anymore, or it will not be banned in the future, but still we have an authorization, and it's strictly or highly regulated in the market. So this is one driver why in Europe hexavalent chromium is under, let's say, replacement for the future. Yes, so what we use, so we have this, our Chrome 6-free tarnish protection. You see some pictures here. We have samples treated with the new Chrome 6-free samples. Before heat treatment, after heat treatment, here we do 140 degrees Celsius, 30 minutes. And you see, if you compare the pictures, you have no discoloration. So the copper stays, let's say, nice and shiny, and it's not oxidizing, so we are protecting the copper in this case, in this test, from oxidation. So we keep the high conductivity of the surface alive. Same is happening if we passivate copper again with our process. We store it at 60 degrees, 90% humidity, and we store it for 30 days. Maybe it's not so easy to see on this picture, but after 30 days, basically, when you look below the blue line, no corrosion, so no discoloration of the samples. So again, in this term, we ensure that the copper is not oxidizing, and we will remain with this high conductivity profile on the surface. Then we have tested we did several comparative testing with this solution in cyclic battery testing. So we constructed small coin cells with our passivated copper. We compared this to standard copper foils from the industry. You see some results here. Basically, we achieved comparable results in all tests, such as discharge capacity. In cyclic testing, every test we did, we achieved similar or same performance. So there's no difference between the copper treated with standard industry or with our new process. We also did some ESI measurements. So we measured the electro impedance of these systems. So we checked how high is the resistance which this passive layer gives to the system, and compared this again with Chrome 6. And here we had even better performance. So the solution we have is even less interfering with the battery than the current technology. Oops. So this offers a very nice alternative, let's say a very sustainable solution to replace a very dangerous chemical with something which is not dangerous. So trivalent chromium, which we use, is not dangerous. And actually, we need this as humans. So therefore, we can easily exchange and have something more sustainable, more environmental friendly. Yes, summary. I'm very fast. Again, we have seen some examples for these degradation effects around lithium-ion batteries. So we have talked on cell and what we can do on the cell level. For example, introduce this new Chrome 6-free passivation for copper. So we protect the copper inside the cell from corrosion. We protect it before it's entering the cell. So there we can improve corrosion for the cell. We have looked on the connectors, the busbars. Here we need to consider how they're connected, which material we use, and then we need to choose the right material combinations. For example, tin, maybe silver. We also need then for these materials corrosion protection to ensure conductivity, to ensure connection and reliability of these different applications, materials. And we also looked on the housings, if we use here different materials, if we use aluminum, if we use steel, what can we do for steel, how we can protect steel from corrosion, what we need to do with aluminum, what are the sequences to ensure here again long lifetime, no corrosion. And there are other fields I didn't touch. Oh yes, we had also here the fasteners, the connections, if you have contact corrosion, if you mix different materials to each other and then you don't choose wisely the combinations, you will have the so-called contact corrosion, which will lead to a very quick failure in your systems. And there are some other fields which I didn't touch, where we also need to consider corrosion protection and surface treatment for these applications. Yes, and with this, there's not only corrosion inside the cell, I showed you, there are different mechanisms inside the cell. There's also corrosion around the cell, so we need to think about the whole system as a package, and let's say as a system, we shouldn't ignore any of the parts we use in these battery systems. And surface treatment can help to deal not only with corrosion, this was the topic, but also with other properties of the materials, conductivity, for example, ensuring quality, paint adhesion, and so on. So this is what we need to consider. That's this. Thank you very much for your attention. I hope you learned something. Maybe you were not aware of this, and I hope I brought you surface treatments as an enhancing, let's say, step in production for your performance. Thank you very much.